All right, so last class we were understanding programming efficiency, and we really were looking at these three methodologies right here. So how to evaluate program efficiency. We thought about the scientists. Don't tell any of the science majors this, but we basically said their way is terrible, but it had certain flaws. Again, there was certain flaws with the timer. Does anyone remember what were some of the flaws that when we were using a timer to try to evaluate a program's efficiency? It was inconsistent. How did we try to deal with that inconsistency? We took the average. So again, that was one major flaw. What was another major one when it comes to using a timer to try to judge your efficiency of your program? Yeah, there's variable, like if you're doing any sort of cloud computing, that's not going to go well. And again, that kind of relates to the other major ones. It depends on your machine. It's really, you're not necessarily judging the algorithm, you're judging the computer who has more money, which of course is not necessarily a good thing when it comes to scientific advancement and things like that. Then we looked at counting operations. So again, what were some of the downsides when we looked at counting? It's harder, which isn't bad. And actually, number 3 is going to take the hard part of number 2 and get rid of it. So that's actually a good thing to say. It's going to take that hard part and get rid of it. So any other thoughts? Remember, it also had issues with implementation. For versus while. That while sometimes will increase more steps because you have to do other variables. It also had things like, what if you had a temporary variable you're using for debugging? So again, when you're counting operations, there's a little different implementations. So that leads us to this last thing that we're going to explore today, the abstract notion of order of growth. So this is what the mathematician or the computer scientist is using to go ahead and understand if their program is efficient. So we ended class, and I kind of left this as an exercise for you at the end of last class. Let's remember what this little function does. It's going to iterate through a list of elements, and if that element is the one we are searching for, it will return true. It returns early. The other scenario, if it manages to get through the whole list and it did not have any sort of comparison it was true, we ended up just returning false. So I left this right here as a little bit of an exercise. Did anyone think through this right here? Everyone's like, if I don't move, he won't know I didn't think through it. All right, so let's go ahead and just kind of look through this. And we have 4 different questions. I want you to take maybe 2 minutes, pair up with 1 or 2 people around you. Bailey, you're on your own kind of a little bit today. You could just run over there for a sec if you want. And just kind of go ahead and talk through these 4 questions. Let me give you maybe about a minute and a half to go ahead and do that. Oh, and by the way, how many steps? That's the same thing. You can think of that as operations. We call it how many operations it'll take.
No, because it's for every single one of them. Oh, no. Wait. So the same one.
Do you want the notes, Jeremy?
So nothing happened.
Yeah, you're right.
All right, let me give you about 30 more seconds. Oh, yeah, question, Anna.
Is that return true supposed to be indented?
Yeah, it should be. Okay, yeah, good catch. So a little bit of a syntax error in here. You know, syntax errors are the best. That should have been indented under the conditional.
Okay. Should return false also be intended one then?
No, because that should happen after the for loop. Because if you manage to get through the for loop, then you'll go ahead and return false because you never found anything.
Oh.
All right, maybe about 30 more seconds.
If it is in there, yeah. So if n is in there in the index, if n is not in there, then L.
Yeah.
And then plus 1.
All right, let's go ahead and see what you guys came up with. I heard a couple of the right things right there. So let's see, how many steps or operations is this going to take? How many who wants to take a shot at that one? Anna?
If n is in the L,
Okay.
it'll be the index of n.
Okay.
Plus 1 for that return true.
Yeah, so you could even see kind of your question. It depends. How many steps is it going to take? It depends, and you said this, on where n is located in the list. Or if it is even in the list. So this is one of those that we didn't look at an example last time where the algorithm can actually end early. So let's think about this. What is the best case? Like, what is the fastest this program will ever run? Anyone figure out what would have been the best case? Exactly, Caroline. So the best case is basically n, the number or the element you're looking for. So n, don't capitalize that, thank you, is the first element in the list. So what that means is if the n is the first element in the list, does it matter even how large the list is? No, because it's going to be the first one. So this is what we would, in this case, the algorithm runs in what we'll look at today as constant time. It doesn't matter if the list has 1 billion or 5 elements. If n is the first element in the list. So then the worst case, what's the worst case?
L.
Go on, what is it? So you say L, Kenneth?
Yeah, if it's not in there, then it has to run through everything.
Yeah, so the worst case right here is basically n is not even in the list. In this case, you have to think about in that case, if it's not, how many iterations here? How many iterations did it have to go through? It would just simply be the length of the list. So we could call the length function on the list. So there's quite a big difference from 1 to 1 billion steps if that was a huge list. And then what is the average case? This one's kind of in between. Anyone? What is the average case?
So it would just be in the middle.
Yeah, the element is somewhere in the middle. And again, this is going to be most of what happens. So you can say n is somewhere in the middle. This, of course, is the practical case to consider. But you know what they say, plan for the worst. So generally, what we're going to focus on is the worst case scenario. So this is, so as we develop this idea of order of growth, we're going to focus on what's the worst case. That is to say that, how long is it going to possibly run? Well, is when we have to go through the whole length of the list. So any questions on this little discussion right here? So we have 3 cases: best case, worst case, and average case. What case are we focusing on?
Worst.
The worst. That is going to be the worst. So what we're going to do is talk about orders of growth. So things are going to grow quite a bit, and what we want to go ahead and do is, and a lot of this is review from last class, we want to evaluate the program's efficiency when the input is very, very, very big. So we're not necessarily concerned when there's only 5 or 10 elements in the list. We're considering extremely large lists. This, of course, is related to asymptotes or asymptotics, which you will remember from calculus. You're concerned about the large case, and we'll look at how that affects and how we can describe that with different functions. So the next thing we're going to go ahead and do is we're going to express the growth of the program's runtime as the input grows. So there needs to be some sort of relationship. So if we consider this right up here, and let's consider the worst case. Let's say to check one element, it took 1 second, and we have a list of length 10. How long will it take in the worst case? If each check took 1 second, it would take, let me say that again. So let's say in this case, let's say let's say the length of the list is equal to 10. And it took each check or each comparison or iteration through this took 1 second. How long would it take for us to go ahead and check? In worst case, it would take us 10 seconds, right? What if I doubled the length of the list? What is it going to do to the runtime? Double it. So it take 20 seconds. So of course, this right here is linear. So if you were to just consider like 15 seconds, it would increase it by 1.5 time. Or a length of 15, it will be increase it by 1.5. So that's kind of what we're looking at right here. What is the relationship between the runtime and the input size? So our goal here is to put an upper bound. So again, this might throw you back to like an analysis course for those of you who have had some analysis, and I think that's where you guys are starting to get to in Calc 2. But we're actually trying to put an upper bound on growth, and we're trying to do that as tight as possible. So what do I mean by that? Let's just say like log of n is bounded by 2 to the n. So if you think about your logarithmic function, is of course, let me get out a pen right here. Your logarithmic function is going to look like this right here. It has an asymptote of 0. Your exponential function is going to grow very quickly. And if you think about this, that the exponential function is bounding it, but is it very tight? Especially like when you're over here, like let's say 10. Like, are these really close to each other? No, it's not a very tight bound. So we actually have a lot of answers for what we're getting to, but we want something that's tight. So what would be maybe a tighter bound on the logarithmic function? So think about what is some other function that maybe isn't quite grow as fast as exponential functions? A lot of options. So x squared, a polynomial function. Yeah, so we can maybe choose some sort of polynomial, like maybe x squared, which would grow a little bit slower. It's still going to bound it, and actually logarithmic is a great goal to get to. If we can get to something that is logarithmic in its order of growth, that's something that is really good to figure out. And if you can actually turn every problem into, if you could find some relationship, there's $1 million prize attached to that problem. I'll tell you about that problem a little bit later. If anyone figures it out, remember to share. Anyway, what was I saying? So a tighter bound would be something, would be a polynomial. So let's just say it could be x squared. You can even look at like square root of x. You can think of some sort of power function as well. And by the way, one thing to note, when I write log 2, I'll say it like this. The common log in computer science is base 2. So if I omit the base in this course, it's not base 10, it's base 2. So just a little kind of funny thing, but again, they're still relatively close. It's just a different base. And as Kenneth, you said, it was hard. That second part was hard. And the reason that was hard is because we were worried about small variations before. So when we're talking about the order of growth, order of would maybe be better thought of as the opposite of exact growth. So we can get rid of small little variations. So it's good to think about order as it's the opposite of exact. So the last point right here, if we're concerned about the order, we're going to go ahead and look at the largest factor in the runtime. That is to say, which sections of the program took the longest to run. So if we look at this program we were talking about up here at the beginning, if we were looking at this return false, this basically loop, which part were we focusing on? I think you all were talking about the loop. You were talking about how many iterations. So again, you're going to be, when you're looking at order of, you're going to be finding the part of the program that seems to be taking the longest. And we're going to look at several examples today. So how do we talk about order of growth? Oh boy, here it comes. We're going to use something known as big, not bug, big O notation. So big O notation measures an upper bound on asymptotic growth, asymptotic. It is also just called order of growth. So a couple things that were used for big O notation. So big O, or, and you'll maybe see kind of what it is more in this, I'm going to put a capital O and I'm going to put parentheses because these are functions. So big O is used to describe, what kind of case are we looking at? Not the best, but the worst. So big O is used to describe the worst case situation. It often occurs whenever the reason we're focusing on it occurs often, and it is the reason for bottlenecks. So if something is not going fast, you got to find the piece of the code that is essentially the bottleneck of the program. It expresses the rate of growth relative to the input size. So when you're looking at a function that has more than one input, you're going to want to think about which of those inputs is causing it to grow or take longer. So if you can see up here above, we had two inputs, but which was the one that was causing it to take a longer time? Was it L or N? L, it was the list. Not necessarily the number we're looking for, it's just the list. So then the last point right here, it evaluates the algorithm. And we talked about this as a warm-up, it does not evaluate the machine. We're not using a timer, we're analyzing the algorithm, nor does it even worry about the implementation. And those were issues that we had with the timing and the counting methods from last class. So let's relate this to what we already know and see the difference between counting exact steps and this order of or big O notation. So take a look at this program right here, fact underscore iter. We assume that n is a non-negative integer, so we don't have to worry about other cases. We set answer equal to 1. While n is greater than 1, we do answer is times equal to n, and then we reduce n by 1. What is this function doing? The fact is a hint. It's your factorial function. This is an iterative implementation of your factorial function. So with that, how many iterations will it take right here? So let's go ahead and just do those counting, and then we'll kind of use big O notation after that. So answer equal to 1, so this is assignment, so that takes 1 step. So that's 1 step. Then this while loop right here, so you have a comparison here. How many steps occurred when we were doing this answer time equal to n? Does anyone remember from last class? That's 2 steps. You have the multiplication operation, and then you have to store it again in answer. So that's 2 operations or 2 steps. And then we also have 2 operations here. Same reason. We have the comparison here. But how many times did this loop occur? Yep, n times. So how many operations? It's going to be a function of n, so 1 plus 5n plus the return. So this is, of course, going to take us 1 plus 5n plus 1 steps. And by the way, just to kind of make sure you're following this, consider if we change the implementation to this right here where we're using a temporary variable. How many operations would this function take if we used this implementation where we added this extra variable? Take a moment and think about that. Anyone think they know? (6n), because you'd have that 1 extra assignment. So in this case, it would take 1 plus 6n plus 1, or you could write this as 6n plus 2 iterations. So remember, We're considering the worst case, so this would be n is just an outrageously large number, and we're considering only about the largest cases. So if n were, let's say, 10,975,000 to the fifth, I'm going to just make it much larger by doing that. Would the 2 even matter? If you're doing 10 billion to the 6 steps, do you care about 2 more? No. Do you even really care if you multiply that number by 6? No, because if you think about it, it is already so big that you really only are going to care about one thing, that n, whatever your input was. So asymptotically, what you would say is that this is big O of n. I meant to say what is big O of, I guess, blank here is what I meant to say. What is big O of blank? So this is going to be kind of alluding to some of the rules. So I'll write it like this. 6n plus 2 is just big O of n. So you could kind of see, what are we doing? We're ignoring the multiplicative and the additive constants. Additive, is that with an I? Yep, thanks Google. Because when n is so large, multiplying it by 6 isn't going to be that big of a deal. Neither is adding 2. So there's that hard part. Like, we just have to really focus on the one part of the program that is making it slow. And again, this is kind of, I asked this question earlier, and I'm going to see if we kind of caught it. If we double the input n, what does that do to the number of operations here? So if you were just thinking about this right here as n, if you doubled that, if you doubled n, if you had 10,000 and you doubled it to 20,000, how many more steps is it going to take? It's going to double it. So again, when you double the input n, and then you almost double the operations, because again the plus 2 doesn't matter, you're going to end up by doubling the number of operations. So if we double the input n, the number of operations also doubles. By the way, this right here is a linear relationship. So what we would say is that this has a linear runtime. So what does big O of n measure? Well, it measures how the amount of time grows as the size of the input or the size of the problem grows. Again, when I say input, basically you could also think about the size of the problem, like if you're talking about a list or something. It measures the asymptotic behavior. Again, a lot of this just some repeats from before, but just to emphasize certain points. It focuses on the term that grows most rapidly. So if we kind of getting down here a little bit, if you're looking at n squared plus 2n plus 1, which term of those 3 grows the most rapidly? The quadratic term, the n squared. So it's really going to focus on the dominant term. So let's see. It focuses on the term that grows most rapidly in a sum of terms. So again, we have a sum down below, and what we'll be looking at is the dominant term, which down in this first example was the quadratic term. So, and this is, like we said above, we're going to ignore those multiplicative and additive constants, since we want to know how rapidly the time required increases as the input increases. So n squared plus 2n plus 2, you can imagine that your algorithm is doing something that is n squared steps, then plus 2, maybe another loop that does like just 2n steps, then 2. So what we would say is that this is big O of n squared. We ignore the additive and multiplicative constants in the 2n and the 2, and we focus just on the largest term, the one that's increasing the runtime as you deal with large numbers. So let's suppose you have another algorithm that is n squared plus, what is that, 100,000 n plus 3 to the 10,000. I don't know really what you would do. That would take 3 to the 10,000 steps regardless of the input. But which of these is the dominant term? N squared, because you think of the largest number that n can be, and that would dwarf the other one. So this is said to be, again, big O of n squared. Now let's look at these right here. So you do have to have some understanding about order of growth, and like hopefully by the time you're taking this course and you've taken some calculus, is you know log base 2 of n plus 4, which of these grows the fastest? The log n. Please no one say the constant. So it's between log n or n. Which one grows fastest? Plug in some numbers in your head. Plug in 2, plug in 4, plug in 16. How many say n? How many say log n? Uh-oh. It is n. Yeah, isn't it? Just by the way, if you plug in n, if you plug in 10, let's say 16, that's 16, but log base 2 of 16 is going to be anyone? Professor Denton? 4. There you go. Wait, is he right? Yeah, yes. So again, we're focusing on the dominant term, the term that grows fastest, because that's what's going to matter when we're dealing with large numbers. So okay, here we go again. So a type of algorithm that you're going to run into a lot, and we'll look at one here at the end of class today, is, let's see, we have 2 terms. We have this, I guess that's 1,000th, 10,000th times n times log n, plus 300n. So which of these grows faster, the n log n or the n?
The 300n, right? Everything else is divided by.
Can you do n squared?
I mean, if you had an algorithm that would be n squared, it would actually, that one would be faster, but the faster term right here, if you think about this, if this is n times log n, think about this n right here. Let me rewrite it like this. Down here below, if you had n log n, compare that with n, and then instead of log n, it's 1. So really you're comparing which one grows faster, log n or 1. The log n grows faster because this is constant. So you're basically just, both of them have n, so divide n out of those, and then you're just comparing the log n and the 1. So this one is actually going to be big O of n log n. That one is bigger than just n. This type of function right here, this n log n, is known as a polylogarithmic function. So it has a polynomial and it's being multiplied by a log, so it's known as a polylogarithmic function. This one will show up a lot in when we look at the divide and conquer algorithms. This shows up quite a bit. And then last one right here. What do you all say? This is big O of what? N to the 30th or big O of 3 to the n? Which is the larger or faster growing function? The exponential or the polynomial? Exponential. Yeah, so this is big O of 3 to the n. This is getting rid of the multiplicative constants, and it's only focusing on the dominant term. So all those little plus ones or like it was, oh, this is 5n and this is 6n, are thrown away when we're talking about big O notation. By the way, now that we've thought about this a little bit, here's the big O complexity chart. So here are your main functions that you'll use when talking about the order of growth. So these, you can see down here is the constant, big O of 1. So you just typically take the smallest constant, so big O of 1, or your logarithmic. Here's linear. Here's, what big O of n log n is actually pretty good. But if you write an algorithm, and we'll look at a little chart down here below, that's polynomial or exponential, or even, God forbid, factorial, these are not going to run fast. If you remember, Fibonacci right here was 2 to the n algorithm, and we couldn't even get like over 30 without standing and staring at it for like 15 seconds. So those functions, those algorithms that are this inefficient are absolutely horrible. Just a couple blanks right here. Let's go ahead and see if you caught it as I went through it. Big O of 1 denotes blank running time. So if it's just 1, did you guys catch what I said that was? That is constant. Log n is logarithmic. Big O of n is a linear running time. Big O of n log n denotes, what did I call it? It's a fun word. Polylogarithmic. So this is a polylogarithmic running time. Logarithmic. And then, of course, n to the c, where c is some constant, is some polynomial time algorithm. And c to the n, where c is the constant. Again, I should probably specify here that c is the constant, or is a constant, is the exponential time. So those are some words that we're going to look at over this class and some of Friday's class. And have you guys heard of the Millennium Prize problems? Some of you have heard it just as you've taken more classes. So one of the Millennium Prize problems is the problem P versus NP. It is P stands for polynomial and NP stands for non-polynomial. And essentially what this problem is doing, is there a way to turn a polynomial problem into something that's non-polynomial? So if you look at this chart right here, we have this polynomial that is an absolutely horrible running time. Could you turn it into something that was non-polynomial, such as like n log n, or even better, something like a log n running time? So it's an unsolved problem. It's been around for a while, and it's one of the 7 Millennium Prize problems. Only one of those have been solved. And if you're unfamiliar with it, do I have the right table right here? Yeah, the Millennium Prize problems. So only the Poincare conjecture, I love saying Poincare, conjecture is solved. And if you solve one of these, there's $1 million prize attached to it. There was Gregory Perelman. I don't know if you guys know this. I think this shows up in maybe an analysis. He was a little eccentric. He basically locked himself in like solitude for years, solved it, and didn't even want the money after he solved it. I'm like, I'll take it. So anyway, that's this big O notation and this idea of P versus NP is a major problem that's yet to been solved, along with a couple other problems. So any questions on what we've talked about so far concerning big O notation? Yeah.
P versus NP, it sounds like the opposite of like Pythagorean or Taylor series.
Maybe. I don't know. I'd have to think through that one a little bit more. My Calc 2 is a little bit on the rusty side. All right. So let's go ahead and consider some properties that we'll use to analyze these programs using big O notation. So here's the math behind some of these. Okay, so in order to analyze programs, we're going to combine complexity classes. So there's going to be a part of the program that is maybe linear, there's going to be a part of the program that is maybe quadratic, and we're going to just have some rules that allow us to combine them and then focus on the dominant terms. So the law of addition is used with sequential statements. So if we look at, we have an example of sequential statements down here. We have this for loop, and then we have another for loop right here. And each of them are going to have their own running time in terms of big O notation. So this for loop right here, oops, let's go back over here. Anyone want to take a shot at this for loop? This is big O of n. Again, we can just look at the input right here is size n, so that is going to be big O of n. And then you have another for loop that follows it. So for j in range of n times n, anyone want to take a shot at what this one would be? It would be big O of, Caroline, you look like you're ready. N squared, n times n. So what we have right here is we have a part of the algorithm that is big O of n, and then we have another part that is sequentially after it. So how would you combine these? Well, big O of f of n plus big O of g of n is simply big O of f of n plus g of n, all in one big O. So it is additive. So that's called the law of addition. So what that means is when we're looking at this in terms of our big O, we have like big O of n plus n squared, and then, well, here I'll write it like this, showing the law of addition. So then that's big O of n squared, which is going to be big O of n plus n squared. And then, of course, inside here, we can apply those same simplification rules that we did above. Which term is the dominant term, the n or the n squared? It's the n squared. So this algorithm right here is just going to be big O of n squared. Because as n becomes asymptotically large, I'm not going to have to worry about this loop. I'm going to have to worry about the loop that's running over n squared iterations. So that is, of course, the law of addition for order of growth or big O notation. Any questions on that one? All right, so let's go ahead and look at the multiplication rule. The law of multiplication is used with nested statements. So we have a similar rule. That is to say, if you were to have big O of f of n times big O of g of n, this is just going to be big O of the product. So it's going to be big O of f of n times g of n, where f and g are just their own complexity class, some function that we described above. So this is an example of a nested program, so just a small part of it. So for I in range of n and for j in range of n. So let's start with this loop, the inner loop right here. So if we look at this inner loop, that is what? Big O of n, yep. So this right here. But if you look at this, we're going to have n loops, and again, this is kind of related. This big O of n is the same as this one right here. So for n loops, you're going to have to do big O of n steps, again, which are just ignoring constants. Like, for example, like if we had more in here, that would basically be ignored. We're just going to do some constant amount of work in each loop. So what does that mean? Well, what we have is this n steps, or n loops, over big O of n. So this is going to actually be the multiplication here. So we're going to have big O of n times n. So that's n loops, each with big O of n steps, which is going to just, well, it's just going to be big O of n squared. So I don't know if you guys will, can anyone think of, I don't know if you guys would know this yet. Maybe you have. Can anyone think of some sort of mathematical computation that you've had to do basically 3 loops for? I don't know if you guys would know this.
You mean like in a program?
Just think through your mathematical career. What is some sort of algorithm you've done? I think there's only 2 of you who have done this. It shows up in Calc 3 where basically you have to do something that's 3 iterations. It wouldn't be L'Hopital's rule. It would be the dot product. So it would be linear algebra. So a common algorithm that would, I'll pull it up here in a minute, so I give you an exercise, that would be have 3 nesting would be multiplication of matrices. So actually cross product. So if you haven't had a linear algebra or Calc 3, those words mean nothing to you yet. All right, so I'm not going to hang out too long there since I think that's only a couple of you. So there's a couple examples of order of growth. Bless you. So just in case you don't realize how bad a polynomial or a exponential order of growth or big O algorithm would take, here's a little table. So if you have an algorithm that is constant, it doesn't matter if n is 10, 100, or 1,000,000, it's always going to take the same amount of time. But if you look at like something like that's exponential, and honestly, by today's standards, that is 1,000,000, right? Yeah, this is a small n by today's standards. We talked about this a little bit about last time, like what are some of the big problems that we're dealing with, such as like searching the internet and image recognition, OCR. This is just a little table to kind of look at how fast some algorithms would grow for larger inputs. So let's do a couple examples, and I'm going to look up that dot product and cross product algorithm in a moment, just to have it for reference. So let's look at this example. The following algorithm performs a linear search on a blank list. And the reason I want this blank is because we're going to talk more about this next week. This algorithm that we've done right here performs a search on an unsorted list. So it's a little bit different than the one we did above, but it's essentially the same process except for doing direct comparison where we're accessing the list by its index. All right. So the linear search, we search a list for some element E. We have a flag right here. Remember, this is a paradigm where this is a flag. And you have I in range of the length of n, and for each of those, you're going to access the list index, and you're going to check if it's the element you're searching for. If it is true, great, but you could keep going. Is there any, if you kind of look at this, what is maybe a quick optimization that you can do? So if you say found is true, but you keep iterating, what's something that you can do to maybe, yeah, you could break, you could return here. Yeah, there's a couple options. You could return true here or break. But at the end of the day, does that actually impact the blank case? By the way, what case are we looking at? The big O looks at what case? The average? The best? The worst. So again, big O is a conversation about the worst case. So yeah, you can do little things to speed this up, but it really does not care if you find it early. Big O is a conversation about the worst case. So list access, L of I, and the length of L. By the way, you can assume that these are constant time. It does not matter if the list, this is actually really counterintuitive. It does not matter if the list is 1 billion elements long or 10 elements long. If you give it the index, it'll be able to do that at the same amount of time. Python is doing some really cool things under the hood called with pointers outside of what we've done a little bit, but it's kind of pretty fascinating that it doesn't matter the list access, whether it's the first or the 1,000th element. If you know the index, it could do it in constant time. And same thing with if you need to know the length of the list, it doesn't need to do any sort of hidden work to figure out the length of the list. It knows it in constant time. Yeah, Anna.
What kind of, how do they do that?
There, it's not iterating through it. So let me give you a moment. I'll tell you in a sec. But while I do that, so if you know that list access and length are constant time, what is the big O, or the algorithmic efficiency or complexity of this algorithm right here? Take a moment and think about it. Big O of, let me give you a moment. Let's see, MIT has a slide that will show you basically why. I debated putting this slide in or not, but we'll do it. Okay, there is a caveat, what I said. Let's see if I can find that. All right, so ask your neighbor what they think is the algorithmic complexity of this one. And then, while I look up this other thing, we have about 5 more minutes left, go ahead and look at this other algorithm and figure out what is the algorithmic complexity of this one. So you guys have all the notes pulled up, right? I want to check for one other algorithm to show you something. No, I'll probably do it next time. Because it'll actually fit with what we do on Friday. Let me ask this then. Anyone think they know what is the algorithmic complexity or the runtime complexity of this algorithm? Who thinks they know it? Big O of Seth, do you think you know? No?
No.
Close. You're definitely dealing with L, but L is the list. So you need a number. Or what about L makes it grow? The iterations right here. going to be, you're close with the L. It's the length of L. So it's big O of the length of L. Or, by the way, this is, again, you could write this also as it is big O of N, where N is equal to the length of L. So this is a linear algorithm, and the fact that we called it linear search was kind of a little bit of a hint right there. This is not a binary search. A bisection search or a binary search is something we'll look at next time. Any questions on that first one? No? Okay. By the way, this is something we'll talk. The algorithm is designed to perform a search on a sorted list. This it actually has the same runtime. So what that I emphasize is sorted up here, but believe it or not, it doesn't matter if the list is sorted or not. This algorithm will take the same amount of time. Why? Because big O is concerned about the worst case. So, so now let's see. We are looking at the worst case. The average case is better. The average case is better. And we're not going to talk about this in course, but the average case, just throwing it out here, that would be big theta. So big O is worst case, big theta is average case, and big omega is best case. So there's that one right there. Try this one right here. So this following algorithm computes the product of integers a and b. What is its complexity? Let me give you a minute to chat it over with your neighbor. This one's tricky because you have two inputs. So don't say big O of n because n is not the input here. Anyone think they know? Let's see. Who haven't I heard from today? Seth, do you want to try again? No? Okay, so if we look at this, which one is causing the bottleneck, the iteration? We're iterating based off of B. Notice here that, again, you're always going to be adding A. So again, this is another way to take a product, just storing the sum. So this is going to be, Kenneth, do you think you know?
Big O of B.
It's just going to be big O of B.
Why can't we just say big O of n? Because isn't it arbitrary what it is?
Well, let's put it this way. If this was like M and N, it's usually a function of the input. Or it's a function of whatever your inputs are. So when you're multiple inputs, you want to go ahead and make sure that you say specifically which of those. Now it is in the linear complexity class. So again, when you're talking about big O in terms of judging a specific algorithm, if it specifies input, your answer is going to be in terms of the inputs of the function. Because the runtime is going to grow with respect to, or an order of B.
Okay.
Yeah. Well, I think we're about out of time. Here's the quick synopsis for you, Anna. The reason that is constant time access is because it's basically just doing math. The caveat is that it's a list of the same size. So like integers, they have to be a list of integers. Like if you have like some are integers, some are floats, some are strings, which are allowed in Python, it gets a little more iffy because those take up more space in memory. But essentially it's a constant time access because there's a formula. And again, remember mathematical operations are constant time. So again, it's basically just doing math. That's constant time. It's not actually iterating to look for it. It's doing some sort of formula. So that's why. So that's kind of like when you find a closed form of a series, for those of you in Calc 2, like, the sum of the first n squares, and you could write that as a formula. It's using the formula, not the actual series expansion. So, and then the reason is also is using pointers, which we didn't talk about a whole lot in this course. But if you're curious, let me know, and we can dig into it a little more. you have questions, let me know. Have a great day, and I will see you all on Friday.